Hello, everyone, and welcome back to the Cisco Optics Podcast, where we talk about pluggable optics for networks. Single-mode fiber transformed telecommunications in the 1970s and 1980s by raising the ceiling for communication bandwidth over transoceanic distances. It took years of R&D to get there, though. Remember, we're sending light through tens of kilometers of glass without regeneration. I mean, imagine how pure the glass of an 80-kilometer thick window needs to be in order to see through it. This is episode 46, and we continue our conversation with Roisin McCool, expert in fiber networks for telecommunications and scientific instrumentation at Corning Optical Communications. We get into optical amplifiers and optical nonlinearity. Roisin McCool is a senior market and technology development manager for Corning Optical Fiber and Cable, specializing in single-mode fiber and access networks. She provides technical and market insight for Corning's global fiber and cable product line management teams. Roisin has 30 years of experience in engineering and optical communications systems and subsystems, including many years designing networks for advanced radio telescopes. Roisin has held project management and coordination lead roles in diverse teams throughout her career. Roisin is the acting chair of the Women in Fiber Committee for the FTTH Council Europe and is the winner of the Corning Optical Communications You Make a Difference Award 2022 for her leadership of diversity initiatives in Corning. Roisin holds a master's degree in electrical and electronic engineering from the University of Nottingham, United Kingdom, and is a chartered member of the Institute of Engineering and Technology. And now join me as I talk with Roisin McCool.
That's how we create our products and how we create differences in the products.
Okay. So back to geography. So you were saying for the highly dense areas where you have like maybe the fiber actually going into someone's apartment, you have this very short bend radius fiber. How about the other type of fiber that you started with, a 30 millimeter bend radius fiber? Is that more suitable for a totally different geography and application?
That kind of fiber is I mean, it's been used in an all-pervasive way throughout many years now. I would say a standard single mode fiber is a very useful low loss medium where you're looking for a transmission medium that is low loss, that's lightweight, that's small, that maybe isn't going to get hit by lightning because it's a dielectric material, that isn't going to be impacted by electromagnetic interference. It's a good fiber. One of the things that fiber manufacturers have done over the years is they've refined that base product to create many products that do something just slightly better than that base product. So, we have the G657 fibers, which are used in environments where you might see bend. We've got even lower loss fibers, like the Corning ULL fiber or TXF fiber. Those are G654 fibers.
Okay.
And those are really low loss. Some of those standards have a large effective area, so it means you can amplify the signal if you're trying to go really long distances. So that G652 fiber is kind of the base. It's the original low loss fiber, and then beyond that, there are different fiber products that have different characteristics for various applications.
You mentioned amplifiers again. Why is that fiber more suitable for amplifiers?
So the TXF fiber has a large effective area. And the reason it's useful in amplified links is that where you get an amplified link, you get a lot of power within the core of the fiber. Some of those amplifiers, they might be, amplifying with outputs of, 10 to 17 dBs on the output. That's a lot of power within the fiber. And that leads to some nonlinear effects. So examples of nonlinear effects would be four-wave mixing, if you've heard of that, where you might have 3 frequencies. And because of the Kerr effect, which is a change in the refractive index because of the power within that fiber, you end up with a 4th wavelength, which then steals power from the others. Other impacts could be scattering effects. Because of the power, that has more impact. And so by having a large effective area, you're reducing the density of the power within the core of the fiber. And that is important because obviously all those examples, the list of nonlinear effects is 4-wave mixing, self-phase modulation, cross-phase modulation, Raman scattering, stimulated Brouillon scattering. All of those are effectively adding to the noise component on the signal to noise of the link. And that's going to impact the capacity of that link.
Because they're, because they're stealing power from the signal. And all those other frequencies generated by the effects that you mentioned basically amount to noise. Because they're the unwanted,
they're all noise.
The unwanted energy.
Yeah. And in fact, they're often described by a power penalty at the receiver, right? So in that way, you're actually describing the fact that the noise is reducing your available signal at the receiver.
Right. So you have to boost the power to compensate for the drop in the SNR.
You want to boost the power often for reach. So obviously fiber is a very low loss medium, but it does have loss. So if you're trying to go hundreds of kilometers, then eventually you're going to run out of signal. So you boost the power with the amplifier. That then creates its own problems with these nonlinear effects with noise. And so the fiber designs around those long haul links are, for instance, large effective area type fibers, these G654 fibers, of which TXF is an example. They have this large effective area to try and reduce the power density within the core of the fiber and therefore reduce that noise.
So does that mean you could have longer stretches between the amplifiers if you reduce the intensity with the larger effective area? Like, do you have the amplification levels available in an amplifier? And really the limitation was the nonlinear effects in the passive fiber.
So there were, in many ways for long haul networks, that is the job of the designer, right? It's to design a network where the powers are balanced sufficiently, and where the number of amplifiers is minimized, because obviously every single one of those amplifier hooks is a location that's using power, its infrastructure to maintain, etc., etc. So there are a couple of ways. The first is with really, really low loss fiber. So the Corning ULL fiber has 0.16, so 0.16 dBs per kilometer, which is one of the lowest losses.
Yeah.
And so that can extend your reach and reduce the number of amplifiers that are required between these spans. But there are other design considerations where you might want one of these large effective area fibers, in order to maintain the capacity, in order to keep the capacity high. the capacity of a network is basically governed by the Shannon's theorem, right? So that is related to the bandwidth that's available. So how much bandwidth you can put across a fiber, how many wavelengths have you got, how many fibers are in the cable, and then the signal to noise. And that is associated with what's the distance, what's the loss of the fiber, how much amplification can we get, and then associated with that, how much noise is in the system. And that noise can come from a series of possible characteristics like self-phase modulation or Raman scattering and those kind of things. And the other aspect then is what is the design on the transmitter and receiver? So what's the bit rate? Is it a coherent system? Are we using polarizations as a modulation scheme? Are we using phase as a modulation scheme? Is there forward error correction at the receiver? So these networks are, extremely complex, particularly when you get into the long haul, because the network designers are balancing all these things to basically optimize the capacity across the link.
Well, let's get back to the fiber itself then. That was the third part of my conversation with Roisin McCool. Next time, we'll get into fiber cabling, connectivity, and density. Hey, we have a new website. It's optics.podcastpage.io. That's optics.podcastpage.io. You can either listen there or use the same podcast platform you've been using all along. Please subscribe. Better yet, leave a review, especially if you use Apple Podcasts. Remember, we're part of the Cisco Podcast Network, where you can find other great Cisco podcasts too. We also have educational videos on YouTube. Just go to youtube.com and search on Cisco Optics. Thank you for listening. This is Pat Chow, Product Manager at Cisco Optics. The next episode is part 4 of my conversation with Roisin McCool. Until next time.